We must remember that the inductor and the capacitor stores energy, the inductor in the form of a magnetic field and the capacitor in the form of an electrostatic charge. Now we've seen that when we take the inductor and the capacitor and we supply it with a range of frequencies due to its formulas, XL equals 2 pi FL and XC equals 1 over 2 pi FC, we will get the following happen. My inductor will generate a linear increase over a range of frequencies. My capacitor, on the other hand, will cause a non-linear decrease. Alright. Now, when these two meet at that very special frequency, that is called my resonant frequency. Now, resonance is that frequency at which the inductor and the capacitor are in harmony, and what that means is the energy stored by the one is transferred to the other one at the same rate. So, as the capacitor charges, the inductor is losing its stored energy and transferring it to the capacitor, and vice versa. The capacitor discharges and that energy is transferred into the magnetic field of the inductor, and that causes that very little energy is actually transferred from the supply. Now, at the resonant frequency, from maths we can see XL, or the graph for XL, is equal to the graph for XC. So XL is equal to XC. Now if we do simple substitution of these formulas, then we see that 2 pi FL is equal to 1 over 2 pi FC. So if I move the frequencies to the one side, frequency squared, that's equal to 1 over 4 pi squared times L times C. And if I then root both sides, I get 1 over 2 pi times L times C. And that is where the resonant frequency formula comes from. That is the frequency, or the formula, sorry, that's a square root. That is the formula that I will be using to determine that frequency for a specific inductor capacitor combination. Now, at resonance, we can see that XL is equal to XC. Now, because this is a series circuit, the current through both of them is going to be equal, and as a result, VL is going to be equal to VC. The inductor's voltage is equal to the capacitor's voltage. If we substitute this concept into the impedance formula, Z equals the square root of R squared plus X total squared. Now, X total is going to be 0 because they are equal. Because XL and XC is equal, we will have a graph Because of this, we can see that when we're working with XL and XC, the closer we get to resonance, you're going to have the effect that the impedance is going to decrease as we approach my resonant frequency. But because my impedance is decreasing the closer I get to resonance, I will get an increase in the amount of current around that same resonant frequency. So as my current increases, it means I'm moving closer to resonance. As I move away from the resonance, my impedance increases, and as a result my current will decrease. And that brings me to the bandwidth. Now, because of the capabilities of an RLC circuit to generate a resonant frequency, we work a lot in radio communication with the concept of resonance. Now, if we just concentrate on the current graph for a second, we see that that graph looks something like that. The closer I get to the resonant frequency, the higher the current flow is going to be. Now the bandwidth is taken at, if that's maximum, if that's the maximum value, then this level at 70.7%. That's called my half power level. Now that level there will determine what my bandwidth is going to be. Bandwidth is between my lower frequency and my high frequency, and that is determined by the formulas. Bandwidth equals F2 minus F1. That's F2 over there, and that's F1 over there. And my resonant frequency is my bandwidth divided by 2. Okay. Another way to calculate the bandwidth is equal to I max divided by the square root of 2. And my bandwidth is also equal to my resonant frequency divided by my Q factor. Now what is the Q factor? The Q factor is the ratio between the energy stored in an RLC circuit and the energy that is released in the RLC circuit. Because we're only looking at resonant circuits, we only calculate the bandwidth and the Q point for a circuit that is at resonance. The Q point calculations we use to determine that 70.7% level. Now the calculations that we use is we say that Q is equal to VL over V total. Okay, VL over V total. But we know that the inductor and the capacitor are in resonance, which means their voltages is going to be equal because their reactances are going to be equal. So I can just as well substitute VC over V total. That's if I want to use my voltage values. If I want to, sorry, that is supposed to be a lowercase q. If I want to use, if I don't have my voltage values, I can use my reactance or my ohmic values. That'll be XL divided by Z or XC divided by Z. So we see in both cases we've got our inductive or capacitive values divided by our total values. Final formula, this is the one that I actually prefer because it's the most simple. 1 over R multiplied by the square root of L divided by C. And those will all allow us to determine the Q factor for our RLC circuit.